Hi everybody, in this video I want to talk about Faraday's law of induction. Faraday's law is of immense practical and technological importance because the overwhelming majority of the world's electricity is generated through methods that leverage Faraday's law. At the same time, it's also important conceptually and theoretically because it illustrates a fundamental connection between electricity and magnetism, two things that people used to think were separate but which we now know are two sides of the same coin. All right, so let's get started. We can ignore all this writing for just a moment. Focus on this picture here. Imagine at some location in space, in some region, we have a magnetic field represented by these red arrows. Imagine in the region in space where I have this magnetic field, I draw a dotted path. That dotted path becomes the perimeter of some area. All right, so it's all imaginary, but there's nothing to stop me from calculating, as a theoretical exercise, the magnetic flux passing through this area. All right, so I have my little bitty bits of area. At each point, I can draw a dA differential area vector, which is perpendicular to the plane of the area at all points. And at each point, I can take B dot dA, add up all those contributions over the full area. That's what this integral says. And I'll get the magnetic flux passing through that area. Great. Faraday's law says something truly amazing. It says that if I have a changing flux, that is, if the rate of change of the magnetic flux with respect to time is not zero, then I'll get an induced voltage as I go around this path. That is, if I start here and increment all the number of volts, then I'll get some number of volts when I get back to there. That's what that says. This symbol is kind of funny. It looks like an E. So sometimes people think it's energy or electric field, but it's just really, it is a squiggly E, but it's the first letter of this thing, EMF. EMF used to stand for electromotive force, but we decided, a physicist long ago decided that's a really misleading name. And so now we just use the initials EMF and don't talk about what it used to mean. But really what it is an induced voltage. Later, when we do circuit problems and we have a calculation like this in a real circuit, this number of volts that we calculate here will have the exact same impact on a circuit as a battery with that same potential difference between the terminals. Okay, so that's why I like to say the way to think of this is an induced voltage. Okay, so let's get back to why that's interesting. If I have a changing magnetic field, that's one way to have a changing flux. Having a changing magnetic field passing through this surface, this imaginary surface that I've drawn, means that if I go along the boundary of that surface, I'll accrue some number of volts. All right, so what is a voltage? Well, remember, electric field has units of newtons per coulomb, but it also has volts per meter. So if I accrue some number of volts by traveling some number of meters, I basically got an electric field. All right, so here's the amazing takeaway from this. It turns out that you don't have to, if you have nothing in a region of space other than a changing magnetic field, you will then get an electric field. It turns out also the reverse is true. I won't go into it here. A changing electric field produces a magnetic field. All right, so we have this deep connection between electricity and magnetism. All right. So now let's go back to the practical. Imagine that I didn't just have an imaginary dotted line here. Imagine that I actually had a wire. Imagine maybe it has some resistance, so it's not a superconductor. We've got a conducting wire here on this path. Well, if I've got the equivalent of a voltage that's been generated by this changing flux, that means I'll get a current. So no battery here. I just have a loop of wire and a changing magnetic field passing through that wire. That'll induce a voltage, which will drive a current. All right, so I'm generating electricity. One way to generate electricity is to have a loop of wire. You don't have to have a battery. Have a changing magnetic field in the region of that loop of wire. You'll generate a voltage. You'll generate a current. You've generated electricity. Amazing. All right, that's the technological basis of the overwhelming majority of the world's electrical generation. Okay, so there's a couple things you might ask. What does the sign of this mean? I've got a minus sign right here. How does that have any significance in this whole thing? Well, so if this is positive, but then I've got a negative sign, this comes out negative. What does positive and negative mean for this voltage that we generate? Well, remember, there's a relationship between the area vector direction and the positive direction around the perimeter of a corresponding path. All right, so remember there's a right-hand rule relationship. If the thumb corresponds to the area vector, the fingers have to correspond to the path around the perimeter. All right, so if the path around the perimeter is this way, if that's the positive path around the perimeter, this would be my dA vector. If I had taken my dA vectors the other way, then the other way around the perimeter would be positive. All right, so once I choose my dA vector directions, choosing them this way, that defines this way around the perimeter to be the positive pathway around the perimeter. Great. This has to do with the positive pathway around the perimeter. If the voltage comes out positive, that would mean that if you had a conducting path, current would go around that positive direction. On the other hand, if this comes out negative, the current would go in the negative direction. So with this choice of the dA vector, this way around the perimeter would be positive, the other way around the perimeter would be negative. So let's work out what would happen if this magnetic field is increasing. So if I have the magnetic field going this way, B dot dA is going to be positive. If the magnetic field is increasing, that'll make my B dot dA bigger and bigger and bigger. So increasing magnetic field through this area would give me an increasing magnetic flux. Increasing magnetic flux would mean that d phi b dt would be positive, but then I've got this minus sign, so this voltage would be negative. What that means is that the corresponding current, if there was a conducting path, would go in the negative direction. What's the negative direction? Well, if this is my dA vector, boom, the positive direction would be this way. So if I had a conducting path here, the current would go the other way because my EMF, my induced voltage, came out negative. All right, that's kind of complicated. There are other ways in practical circuits to work out the directions, something known as Lenz's law, which I'll talk about in another video. Okay, there's a couple things I need to say that are important. In electrostatics, the electric field is the negative of the gradient of the electric potential. Well, these kinds of electric fields produced by this Faraday's law, electric fields produced by changing magnetic fields, don't obey this relationship. This is part of it, but you have to add some other things that are beyond the scope of this course. There's something called the vector potential. We won't address that in this course, but it's something that has to be tacked onto this to go from electrostatics to this more general thing that we might call electrodynamics. All right, so I hope that helps introduce Faraday's law. Thanks for watching.